Hello everyone, my name is Maryam El Fiti and I am a PhD student at Mohamed VI Polytechnic University at Green Tech Institute. I am delighted to be among you today to present my work entitled Thermal Performance Enhancement of a Longitudinal Fan Latent Thermal Energy Storage Unit. So, this is how the presentation will unfold. First, a brief introduction about the motivations and the objectives of the study will be discussed. Second, we will present the materials and methods employed in the current study, after which the numerical results will be presented and discussed. For finally, conclude the presentation with some perspectives. Well, nowadays, environmental and energy issues are an international concern. Meeting the growing energy demand while reducing greenhouse gas emission is a major challenge. In this context, industries, as one of the most energy-consuming sectors, are forced to improve the energy efficiency of their processes. One way to achieve this goal is by integrating waste heat recovery systems such as thermal energy storage. Latent thermal energy storage is a promising solution that has worthwhile characteristics including high storage density, the capability to restore energy at constant temperature, and so on. However, the main drawback of the PCM-based systems is the low thermal conductivity of the phase change materials. In this study, we attempt to provide a good understanding of heat transfer during the charging cycle by numerically simulating a coaxial PCM regenerator. To achieve this, we will study the effect of natural convection as a key mechanism in the melting process. Finally, we will numerically investigate the role of adding fans in improving the thermal performance of the regenerator by comparing two cases, a fanned and a fanless unit. In our study, two-dimensional horizontal PCM-based regenerator is investigated. The system consists of an inner stainless steel tube with 20 mm in diameter and an adiabatic shell with 40 mm in diameter. The annular space between the shell and the inner tube is filled with PCM, which is in our case paraffin wax with melting temperature of 55 degrees C. The numerical solutions are obtained using the commercial software Ansys Fluent, which is based on the enthalpy porosity approach and the finite volume method. In order to check the accuracy of the solution, prior calculations were conducted, in which we examined different computational grids as presented in Figure A and different time steps as presented in Figure B. Based on this independency test, we chose 0.1 mm in the grid size and 0.1 per second in time step. And to study the effect of natural convection of the PCM melting inside the regenerator, two case studies are simulated and compared, with and without consideration of natural convection. The following figure illustrates the evolution of the melting interface, the velocity vectors, and the temperature distributions of the two cases. When the natural convection is considered, three stages are observed. At the very beginning of the process, the PCM is completely solid, and the heat transfer is only governed by conduction. At this stage, the natural convection has no noticeable impact on the melting process. After a few seconds, the buoyancy forces are more obvious. Therefore, the density difference between the hot and the cold PCM drives the fluid to flow towards the top region, forming natural convection, and thus accelerating the melting rate. At the last stage, conduction heat transfer mechanism prevails once again, leading to a decrease in the melting rate. While when natural convection is neglected, only conduction heat transfer mechanism is involved, leading to a uniform temperature distribution and annular shape liquid-solid interface. Therefore, the melting rate is slow compared to the case with natural convection. And to study the effect of fans on the thermal performance of the PCM regenerator, two cases are simulated and compared, a fanless and a fanned case. Initially, as the heat transfer is governed by the conduction, a thin layer of liquid PCM is developed evenly around the hot tube and the fans. At this stage, we don't notice any remarkable difference between the fanned and the fanless unit. As the melting process progresses, natural convection takes place, leading to fast melting, and we start observing a marked difference between the two units. At the last stage of the melting process, the liquid fraction is higher in the fanned case due to the downward fan that conducts the heat to the bottom, which is a hard melting region. To take further insight onto the effect of adding fans to the regenerator, the temporal evolution of the liquid fraction of the fanned and the fanless cases are compared, as plotted in the following figure. From the curves, we can see that the fins allow faster melting. Therefore, the addition of fins can reduce the melting time by up to 46.3%. As a conclusion, we can say that the use of longitudinal fins can considerably promote the melting process. Therefore, a reduction in the total melting time of 46.3% is achieved. Moreover, the results indicated that the natural convection improves considerably the melting rate of the PCM and leads thus to an enhancement in the thermal performance of the regenerator. As perspective, more attention should be paid to an optimization of the fan parameters. To here, we come to the end of our presentation, and thank you for your attention.